We're going to be doing lots of stuff with Mathematica today, like I did with last class's notebook. I will say that Moodle, but you may want to write down as much as you can as far as Mathematica details. I probably will have you do some Mathematica stuff for the next assignment. Maybe a printout or two, maybe something to turn in electronically as well. In lecture A, we'll continue with the harmonic oscillator model. We will include friction this time as well. Talk about the phase plane for that, and include various vectors in Mathematica. Those vectors include the background vector field for the phase plane where the solution curves travel through, indicating how the mass in a spring moves over time. But I'm also, just to emphasize concepts that we talked about at the beginning of the semester, I'm going to put velocity vectors, position vectors, velocity vectors, and acceleration vectors into the picture as well, because these are parametric curves. Even though those position vectors, velocity vectors, and well, especially velocity and acceleration vectors may not have much meaning in terms of the actual mass on the spring. Or it might have meaning, but it might be hard to interpret. Then in lecture B, we will look at more complicated models that involve nonlinearities. And because of these nonlinearities, they will be really impossible to solve by hand. We'll have to just approximate answers in Mathematica. Those are called interacting species models and their phase planes. All right, so for the harmonic oscillator, again, the simplest situation to think about with the harmonic oscillator is a mass and a spring. Harmonic oscillators come up in other areas too, like electronics, for example, where instead of looking at the position of a mass on a spring, you're looking at some voltage that's going up and down over time. But it's sort of easiest to think about with a mass on a spring. Here you have a mass, here you have a spring. Before I said this was ice, I said this was in a vacuum to keep the friction to a minimum. Now I'm going to allow for friction. So, it still would be nice if this were ice, if it were sliding on ice to still minimize friction, but it doesn't have to be ice. It's just a floor. This is still a wall that it's attached to. It doesn't have to be in a vacuum anymore. You pull the mass, let it go from its rest, from some non-zero position perhaps. This is position 0 right there. This is not the origin right there, that's the corner of the floor and the wall. The origin on the x-axis I'm taking to be the equilibrium position of the mass. I pull it, I let it go, or I hit it with a hammer, give it some initial velocity, see what happens. Because of friction, it's going to oscillate perhaps, but those oscillations will get smaller and smaller until you can't tell that it's even moving anymore. Actually, if the friction is high enough, it won't even oscillate. We will see. What are the forces on the mass? Well, there's Hooke's law's force, the restoring force of the spring. Again, when you pull the spring, when you make x positive, then the restoring force is in the negative direction. If you compress the spring, push the mass toward the wall so that x becomes negative, then the restoring force is in the positive direction. It always has the opposite sign that x does, and Hooke's law also assumes that it's proportional to x. There's some constant of proportionality where that's the restoring force of the spring. Is Hooke's law perfectly accurate? I'm not positive, I don't think so. I think it especially is not accurate if you pull the spring too far. You effectively break the spring or compress it too much. Then I think it becomes invalid. But it's a decent model, at least for small oscillations and reasonable springs. What about the friction? Sometimes called the damping force is what I'm going to write next here. Damping force, also known as friction, that can come from lots of sources: the floor, the air, the internal friction of the spring, the molecules of the spring sort of causing friction. So it can come from lots of sources. What is that friction equal to, that frictional force, that damping force? Again, you think simple, you try to keep it as simple as possible. it should make some sense that it should be proportional to the speed, in absolute value at least. The absolute value of the friction, the damping force. The faster you go, the more the friction should affect the motion. That would be the simplest model. It sounds like the simplest model is to assume it's a linear function of the speed or the velocity. And velocity having a sign, your friction, your damping force should be in the opposite direction of the velocity. So if the mass is moving to the right, that's the positive direction, the velocity is positive, the damping force points to the left. Even when the mass is over here or over here, it doesn't matter the position of the mass. If it's moving to the right, the damping force is to the left. And if the mass is moving to the left, then the damping force is to the right. If the velocity is negative, the damping force is positive.
So, question?
Mm-hmm.
So then what's B? Is B just an arbitrary constant?
K and B are constants of proportionality. They're not arbitrary. They will equal certain things for certain situations. So K is called the spring constant. It's related to how stiff the spring is. So if you've got a real, thick spring, so to speak, real heavy duty, K is large. And not so heavy duty, like a slinky maybe, at least for small oscillations, K would be small. Damping, the B is the constant there. If there's a lot of damping, a real rough floor, so it's still got to be able to move somewhat. Real thick air, high air pressure. Lots of internal friction, then B would be high. In the situation where we have ice and a vacuum, there's still internal friction from the spring, then B would be low, close to 0. By Newton's second law, N2, my abbreviation for Newton's second law, this equals the mass times the acceleration. And because, again, the acceleration is a derivative, it's the first derivative of velocity. It's also the second derivative of the position. This is a differential equation. Since you ultimately want to know the position as a function of time, it's best to get this completely in terms of the position x. Although when we write the system, we'll get back to velocity anyway. It's traditional to replace v with dx dt. And it's also somewhat traditional then to rearrange this equation so that 0 is on one side and all the other terms are on the other side. We can add kx and add b times dx dt to both sides. And we can ultimately write our equation like this. M times the second derivative of x with respect to t plus b times the first derivative of x with respect to t plus k times x equals 0. That's a common way to write this second order equation. It's also common to divide everything by m. Like this. And it's also a common thing to replace b over m and k over m with different letters. In the book I use for differential equations when I teach that, the book calls this p and this q. Okay? Just to make things look simpler is the idea. But you want to always remember that p is b divided by m and q is k divided by m. But it makes things look simpler. I mean, you could take the mass to be 1 kilogram to keep things simple, and then b would equal p and k would equal q if m was 1. Second order equation, can Mathematica solve it? Yep. Though if you leave the parameters in there as arbitrary, I think it will look very complicated when I try to solve this. So if I try to use DSolveValue, actually let's go ahead and type it in without dividing by m. Let's keep the m in there at first, like this. M times x double prime of t plus b times x prime of t plus k times x of t equals 0. Let's add in arbitrary initial conditions. X of 0 equals x0. X prime of 0, the initial velocity equals v0. Solve for x of t, and t is the independent variable. I think this will produce an answer, but I think it's going to be pretty nasty looking. Let's see what it does. Yeah, very nasty looking. And actually, a subtlety that you don't see in this is this actually can involve complex numbers. V squared minus 4 times k times m could be negative. And the square root could be the square root of a negative number, which is an imaginary number, and ultimately this would be then a complex valued function, not a real valued function. And you might wonder, how is that useful? How can that be interpreted? I mean, couldn't b squared minus 4km be negative for certain choice of b and k and m? Yes, it could be. If you take diffq from me, we'll see that that can actually be interpreted in terms of real functions using something called Euler's formula, which I mentioned here, I think, didn't I? E to the I theta is cos theta plus I sine theta. Did I mention that here? It's related to that most beautiful equation. You can use that equation to interpret this in terms of real valued functions. And in fact, it's exactly in the case where b squared minus 4km is negative that you actually do get oscillation, even if the oscillations die down. You do get cosine and sine involved. But in general, it's pretty nasty here. We can make things look a little simpler if we make the n equal to 1. That's a little bit simpler looking. And of course, in various situations, you can plug in certain values for, in this case, b and k. What would make the square root come out nice? For example, if b were 5 and k were, let's see, b were 5 and k were 6 would come out nice. But it would not involve trig functions. It involves just exponentials. And it's actually exponential decay, which you can't quite see unless you expand it. Actually, exponential decay there. So there's no oscillation in that case. If b is 5 and k is 6, that damping is enough that it causes no oscillation. There's no trig functions in there. It would also come out nice, I'm trying to think on the spot here. If I'm trying to come up with an example with oscillation as well. I wonder if this comes out nice. Oh, not real nice. Trying to calculate b squared minus 4k in my head to see if we get a nice negative number that's a negative of a perfect square. Doing these kind of calculations in my head is not my forte. Okay, that's pretty nice actually. If b is 2 and k is 5, yeah, okay, b squared minus 4k would be negative 16. Okay, that comes out nicely, and it does involve trig functions. So if b is 2 in this case, we do get oscillation. But the oscillations die down because they're multiplied by an exponential decay. Okay? So you can use DSolveValue on the original second order equation, but our main goal today is to get to the system and the phase plane. Essentially looking back at this one being equal to that one and dividing everything by m, well, actually look at this one compared to this one and divide everything by m. Essentially that gives you your system of equations along with the fact that the velocity is the derivative of the position. So I'm going to write a system of differential equations here. The first of which is the fact that the velocity is the derivative of the position. The derivative of x with respect to time is the velocity. That's the first equation in my system. The second equation in my system is for the derivative of the velocity, which is the acceleration, but I want to get that in terms of x and v. Use the fact that this equals this and divide everything by m. So I will get negative k over m times x minus b over m times v. You can also then, once like I did before, you could replace b over m with p and k over m with q. You could also write this as dx dt equals v, dv dt equals k over m is replaced by q. You get negative qx, and if b over m is replaced by p, you get minus pv. There's a system of differential equations. Let's take this example, this last example that we just did, and have DSolveValue solve it as a system. This is one second order equation, because it involves a second derivative. This is a system of two first order equations because they involve first derivatives, but they're equivalent to each other. X as a function of t is going to be the same in both cases. What can I do to get this in here? Essentially, the x prime initial condition needs to be replaced by v. We're going to solve not just for x of t, but both x of t and v of t. You solve systems simultaneously. You're solving for both quantities. And the second order equation here needs to be replaced by two first order equations. X of t is v, so x prime of t equals v of t. And v prime of t equals what? It equals that. I'm taking m to be 1, b to be 2, and k to be 5. So I'm going to replace this by negative 5x minus 2v for this example. Negative 5x of t in Mathematica minus 2v of t in Mathematica. You need to put the t's in there in Mathematica. Don't put the t's in there by hand. There's a good reason for that. Do put them in there in Mathematica. All right, it is the same situation, same thing. The x of t that this solves for should be the exact same thing that I got with this one. But there will be another function, there will be v of t, that I'm also solving for. That will be the derivative of x of t. So first of all, compare this with that. They are exactly the same. See that there? Comparison. Let's also check that the derivative of this is that. I can use the d operator to differentiate. I don't know if I've shown that to you before. Have I showed you capital D before? That will differentiate this with respect to t, and then I can maybe do expand or simplify or something, and hopefully it gives you the same thing as this. And yes, it does. Okay? So this is giving us both the position and the velocity at once. And then in the phase plane, you graph that corresponding parametric curve in an xv plane. That's the idea. Is it okay if I don't write all that out by hand? That's by hand, it's an x of t comma v of t. It's a parametric curve. I can use ParametricPlot to plot it. I'll do that now. Let me go ahead and call this c sub x0 comma v0 of t. So I'm going to copy and paste the solution in here, right there. And it is a list in Mathematica, which I'm going to interpret as a parametric curve. That I can then plot after it's entered with ParametricPlot. I'd like to animate it, allow myself to change the initial position, initial velocity, and also let the time change so I see the motion. I'm ultimately going to combine this plot with other things, so I'm ultimately going to use show as well, but let's initially just do ParametricPlot. Take this a step at a time. Inside manipulate. Let me go ahead and put my manipulate parameters in there first. There's my B parameter, which is time. Starting out just barely positive and ending at, say, 1 period of motion. In the phase plane here, you see 2 t's in the cosines and sines. The period of those as functions then would be 2 pi divided by 2. Pi would be 1 period of the back and forth motion of the mass in the spring, and also 1 period of a periodic solution in the phase plane that will look like an oval, like we saw the other day. So if I go to pi, that should be good enough. I'll show you how to make pi before. I think so. Escape P, escape makes it pi. You can also do capital P, lowercase I. Then I'm plotting C, this parametric curve, C sub x0 comma v0. Okay, I guess I was going to say what x0 and v0 do. Let's start the initial position out at position 1. Let it go to -2 or as high as +2. Let's start the initial velocity out at 0. Let it go as low as -2 and as high as 2. That's what that syntax does. Let's also keep the plot range fixed. I need to give a t interval. T goes from 0 to b. Keep the plot range fixed inside parametric plot here. Maybe -4 to 4. Okay, this is going to give us a basic graph. Letting time go by gives me that. Interesting, it's not an oval, is it? I made a mistake. I was thinking of the oval from the last class. There was no friction in the motion, so it was a periodic solution. Here, I forgot we had friction. X and V are going to go to 0. The mass is going to come to equilibrium. So we don't get an oval and ellipse, we get a spiral. But after pi units of time, it is coming back to being where the velocity is 0, the velocity is the vertical axis here, and the position is some positive local maximum. I think it is worth labeling the axes here. To emphasize, the horizontal axis is x, the vertical axis is v. Here's how you do that. So this is a solution curve of the system of differential equations in the phase plane, it's called. It's not showing you the motion of the mass, right? The mass doesn't spiral. It goes back and forth. At any moment in time, this tells you, at that moment in time, in this case about 2.879 seconds, for this situation, the mass has position, about 0.03 or something meters, 3 centimeters on the right. And velocity at that moment in time, positive 0.03 as well or so. approximating there. Maybe 0.05. So what is the motion doing? You're pulling it 1 meter from the rest position, letting it go. Immediately, the velocity becomes negative, meaning it starts moving to the left. And x decreases from 1 down towards 0. The mass is moving to the left. It's moving to the left the entire time this curve moves to the left, because x, the left-right coordinate, is the same as the x for the mass. So the first coordinate at this point is always the location of the mass on the x-axis. Goes past equilibrium. At this point in time, it turns around to start coming to the right. The velocity becomes positive. But the velocity is getting close to 0, so it's not moving very fast anymore. Okay, because of the damping. We want to add more to the picture. We want to add the vector field. It's an analog of the slope field with scalar differential equations that are not systems of equations, first order ones. We made slope fields, and solution curves had to follow the slope field. For systems of two equations, two first order equations like this, we can make a vector field, and the solution curves have to follow the vector field. I didn't really dwell on how to understand what the vector field, how to make the vector field the last time. I will spend a few minutes with that today here. So I'm going to show the parametric plot with a vector field plot made with VectorPlot. I'm going to color the solution curve thick and red here. You always want to put the vector plot first so that it's in the background and the solution curve is on top of it, so to speak. Because if you did the solution curve first and then the vector field, it might cover the solution. You want to see the solution. You want to see them both. So put the vector plot first. With slope fields, we put a 1 in the first spot before the comma, and then the right-hand side of the differential equation after the comma. With vector fields, for systems of differential equations like this, you put the right-hand sides in both spots. The right-hand side of the first equation before the comma, the right-hand side of the second equation after the comma. The right-hand side of the first equation is v, so put a v there. The right-hand side of the second equation, looking here or there, is negative qx minus pv. Where again, for our example, what's q and what's p? Back up there. Negative 5 is the q, negative 2 is the v, is the p. Essentially, I need to type this in without the t's. Put the t's in there for DSolveValue. You don't put them there when you write this by hand. You also don't put the t's in there when you do the vector plots. The vector plot doesn't know you are interpreting this in terms of differential equations. You can make vector fields without thinking about differential equations at all. So as far as the vector plot is concerned, it has no knowledge about the fact that you're going to put solution curves of a differential equation on there. It just wants to make a bunch of vectors based on the coordinates of x and v. So you need to put these things in there without t's. So negative 5x minus 2v, no t's. Negative 5x minus 2v. Give a range of values for both x and v, with x first, v second, because x is the horizontal axis, v is the vertical axis. So x comes first. X goes from, say, negative 4 to 4. Then v comes next. V, say, goes from negative 4 to 4 as well. Do not switch the x and the v around there. Don't put v first on x second. Let's see what this looks like. It's not too bad. it is showing arrows that are representative of the vector field. These arrows are actually too short. I haven't said how to make vector fields yet, though, so you wouldn't know that. The solution curve does follow it, though I don't know why it's stalling so much. It's hard to tell when it's close to the origin. We should probably zoom in closer to the origin here to see this better. So let's go -2 to 2 for all this stuff. So you can hopefully see those vectors better that it's following. A little bit better. Again, I don't know why it's stalling so much. It's usually not. This is not typically a situation where it stalls in so much. How are the vectors in the vector field determined? What is going on there? The solution curve follows the vector field in the following kind of way. Anytime a solution curve touches the base of one of these vectors, that vector is a velocity vector for that solution curve at that moment in time. Meaning, the solution curve is tangent to that vector at that moment in time, and the length of the vector equals the speed of the curve. Not the speed of the mass on the spring, the speed of the curve in the picture. Which you can think about without thinking about masses on springs at all. You can kind of see, if you imagined arrows in here, this curve would be evidently tangent to those arrows whenever it touches one of them at the base. This arrow looks like the one it gets closest to right there. But these arrows are too short. They have been scaled down by Mathematica. They are not long enough to have a length equal to the speed of the motion of the curve. Why? Because if you made them the right length, it would get, the picture would be too messy. That's why. It's also the case that many times people, instead of making a picture of the vector field with scaled down vectors, though relatively the right length, I mean, this vector right there is like twice as long as that vector right there. So that would represent a velocity vector twice as long as this one. The curve, when it touches this one, would be moving twice as fast as the curve when it touches that one. So they're proportional to the right lengths relative to each other, but they are all too short. You can instead make something called a direction field, which just shows the directions and makes all the vectors the same length. So you see directional information, but you lose speed information in the picture. But it is a prettier picture to look at. And you can get Mathematica to implement that by adding an option with the vector scale here. Vector scale arrow, like for example 0.03, none, should work. Yeah, that's making them all the same length. So we see the directional information better, though we lose the velocity speed information. The vectors are getting shorter as this heads toward the origin because it's slowing down. You see the curve slowing down. Let's add even more to the picture. Let's get rid of the frame. Frame, arrow, false. Adding axes. Axes, arrow, true. We lost them when we did the vector plot. I also want to do one more important thing. So we now got rid of the frame and we see the axes back in there. I also want to add a big dot into this picture before right here. I'd like to put a dot, a big dot, for extra emphasis.
at the origin. Now you see a little arrow near the origin there. That is actually not the arrow that would be based at the origin. The arrow that would be based at the origin for the vector field would actually be just a dot, an arrow with no length, because when x and v are both 0, the right-hand sides of these equations are both 0. The derivatives of the solutions are 0 all the time. The solutions are constant functions. If your mass starts at equilibrium and you don't give it initial velocity, it doesn't move. The equilibrium position for the mass corresponds to a dot in the vector field called an equilibrium point or equilibrium solution for the differential equation. And equilibria are very important to emphasize in these phase planes with big dots, whether you do it by hand or in Mathematica. On Mathematica, you can make these big dots with, for example, list plot. If you want to make a big dot at the origin, you can do this. Make a big black dot. There it is, a big black dot at the origin. I've never shown you this syntax before, I don't think. That's a way to make a big black dot at the origin. That is an equilibrium point for this phase plane. It corresponds to an equilibrium solution. X is always 0, v is always 0, a constant function that solves the differential equation of the system. Corresponds to when the right-hand sides of these equations are both 0 algebraically. The only way these are both 0 is when both x and v are 0. Let's take our break.